In this example, we've been asked to find the linear approximation to this function at this point x1 equals 0. So I think to myself, a linear approximation is a straight line that approximates this curve close to this central point. To find the equation of a straight line, I need two things. A point, x and y value, so here's an x value. I can substitute that in here to find the y value, the coordinates of the point, and I need a gradient. The straight line we're talking about that is used as the linear approximation is the tangent to this function at this point. And so to find the tangent, I need the derivative, which would give me the gradient of the tangent, which is my straight line, and a point, and so I can do my work. You might be able to remember the formula for the linear approximation, which is this: y is equal to the function evaluated at x1 plus the derivative f dash evaluated at x1 multiplied by x minus x1. So you can see all you need to do is substitute x1 into the function and substitute x1 into the derivative of the function, and that's the equation for the straight line. If you can't quite remember the equation for the linear approximation, you might think of this graph and where the equation of the tangent comes from. So on any function like this, y equals f of x, I've been given a point. Here it is here, x1. The y coordinate of that point we can label y1, which is equal to the function evaluated at x1. The tangent at this point would be the straight line that comes through, touches the function at that one point x1, and continues on. So it is the equation of this tangent that I want. I know that the slope or the gradient of that tangent, which I can label m, is equal to the derivative of the function evaluated at x1. So once I have all these values, the x1, the y1 value, the gradient at x1, then I can use the equation of a straight line. So the equation of this tangent, which is the standard formula, y minus y1 is equal to m outside of x minus x1. If I rearrange that, substitute f dash of x1 for m, and substitute f of x1 for y1, take the negative y1 over to the other side of the equation, substitute these two quantities in, you will see that you get the same formula, y is equal to f of x1 plus f dash of x1 times x minus x1. So you can see that is where the equation comes from. If you can remember the formula, you can go straight for that without the picture, but I think the picture gives you a good idea of what's going on. So I know what my function is. F of x is this cubic here. I know the value x1. So I need a couple of things. I need to differentiate the function and substitute in x1 equals 0, and I need the function evaluated at x1 as well. So we can just work out each of those things. Start with the function evaluated at x1, which is the function evaluated at 0 in this case. Substituting that into the cubic up the top, you can see all the x values will be equal to 0, and we'll be left with minus 1. So f of 0 is equal to minus 1. I also need the derivative of the function and then evaluate it at x1. So differentiate the function first. F dash of x is equal to, I'm differentiating the cubic, derivative of x cubed is 3x squared. The derivative of plus 3x squared is plus 6x. The derivative of plus 2x is plus 2. And of course the derivative of minus 1 is 0. So there's the derivative of the function. For my linear approximation, I need that to be evaluated at point x1. So f dash of x1 is equal to f dash of 0 at this stage. Again, you can see the x terms equate to 0, and you've just got a value of 2. So with the function evaluated at x1 and the derivative of the function evaluated at x1, I substitute into the equation for the linear approximation, which gives me y is equal to f of x1 is negative 1 plus 2 outside of x minus 0 for the value of x0. Rearranging this, you can see that the linear approximation of the cubic, which was given to us at the point x equals 0, is y equals 2x minus 1. So now a further question might be to demonstrate how good the approximation is. So there's the linear approximation to this cubic at this x value. So now if we to test how good our approximation is, we might be asked to evaluate both the function and the linear approximation at a value of x. So just as a side note, if we were to substitute in a value, say x equals 0.1, we're going to test how close the linear approximation is to the original function. So substituting this into the linear approximation, I'll get y as 2 times 0.1 minus 1, which gives me a value of negative 0.8. Comparing that to the function evaluation, so I'm going to substitute 0.1 cubed plus 3 times 0.1 squared plus 2 times 0.1 minus 1. If you go through and do that, then the function evaluated at 0.1 gives you a value of minus 0.769. Using a calculator for that one. So that's a pretty close approximation. Our linear approximation of 2x minus 1 gives us a value negative 0.8. The function is evaluated at 0.769, negative 0.769, and they look pretty close. If we move further away from our central point, so just as another note, at a point, say, x equals 1, substituting that into both the linear approximation and the function, the linear approximation gives us a value y equals 1. The function evaluated at that point 1 gives us an answer of 5. You should check that, make sure you get the same answer. Looking at those two, the linear approximation is not a good approximation of the cubic or of our original function at the value x equals 1. So as we move further away from the central point, we can see our central point at x1 equals 0. If we're close to the central point, we get a pretty good approximation. As we move further away, we get a terrible approximation.